All right, welcome everybody. Today we're going to be talking about foliar feeding and a little bit deeper insight into some of the aspects around formulation and how that can impact droplet quality and droplet performance. So we're going to take a little bit of a focus, a bit of a case study perhaps on a few deeper insights into the role of molasses also. So, okay, let's dive into some general info about foliar feeding, and then we'll get into some practicals on how to design a good foliar spray. So, why foliar feed in the first place? Well, there's a couple of good reasons, multiple good reasons really, and some of those include that we can achieve higher nutrient use efficiencies with foliar feeding as compared to soil application. And I stress a caveat here that we're not necessarily suggesting to replace soil-based feeding, but we are looking at foliars as a strategy to complement that soil feeding. There are strengths, there are pros and cons to both approaches, but that one of the kind of the key angles around the foliar is that because we target the application of the nutrients directly onto the foliage, therefore, we are achieving greater efficiencies because we are reducing some of the losses that come through soil-based application, some of the lockups, antagonisms, that kind of thing. So therefore, by improving the efficiency, that does mean that we can start to use less input. So there's going to be an economic gain, a financial improvement there through foliar applications as well. Look, they can also improve yield, quality, plant health, other metabolic growth processes of plants. And really one of the strengths of the foliars is the timing of those applications. It's the ability to target the timing of that application and link that to crop development stages, plant developmental stages. So it really opens up some really more precision timing approaches as well. Again, because we're reducing some of the nutrient losses from the system, that can improve environmental outcomes. And here, of course, we're particularly talking about things like nitrogen, which is a very leaky nutrient, nitrogen as well as phosphorus that starts to have some negative impacts in the environment, particularly in our waterways. And we also have opportunities to improve the nutrient density of be that the food or the feed that we're growing. And that can have animal performance benefits or human health outcomes in terms of nutrient-rich food and feed. So, okay, just a quick point here about the soil. And again, with the caveat here, we're not suggesting to replace soil-based feeding, but it's just the reality that we can't assume that just because nutrients are present in the soil, that they're actually going to be taken up. There are many factors down there in the soil, many interactions that can limit nutrient uptake even when nutrients are present in the soil. And so we have some obvious things like high temperatures, kind of temperature stress on the plant, but also high temperatures that dry out the soil, so soil moisture. So if we don't have good moisture in the soil, of course that's going to be a bit of a limiting factor to some of that nutrient draw through the soil water. We have other soil extremes like pH extremes or salinity or sodicity issues, for example, that could be also limiting factors, or other things like nutrient lockups, where again the nutrients are present, but they're just bound tightly and locked up with other nutrients and therefore rendering them unavailable. But we also have other than, say, biotic stresses on the plant. So if the plant is under pest or disease attack, for example, it's got other problems to deal with and nutrient uptake can be impaired. And also where soils are, again, not functioning from a biological point of view. If we are limiting in biological activity, then nutrient supply is also going to be limited through some of those microbial mediated pathways of nutrient uptake. So point being here, you've got a range of environmental factors, soil factors. All of these ultimately can limit uptake of nutrients or root function, even though the nutrients might be present in the soil. And a quick example of nitrogen there, as I alluded to just previously, it is a particularly interesting case study and example because it is such a leaky nutrient, more so than probably any of the other nutrients. And it does have this tendency to off-gas into the air. So that can be off-gassing as ammonia or nitrous oxides. But of course, nitrates in the soil can also leach down through the soil into our groundwaters, into the rivers, into our waterways, etc. So nitrogen is one particular example is such a leaky nutrient, and these losses create those inefficiencies. And that's where the foliar feeding can increase nutrient use efficiency, because if we bypass the soil where these losses take place, if we bypass that and put that nitrogen directly into the leaf, into the plant, well, we're bypassing these losses, we're minimizing these losses. And when you start to lose less from the soil, you can start to use less from the bag. And that's again where those economic advantages can then creep in. So, okay, yes, plants have evolved roots for a reason, and that's to take up nutrients from the soil. And yes, nutrient uptake from the soil is the dominant pathway of nutrient supply. But plants have also evolved various mechanisms for taking up nutrition through the leaf, and we have many examples of this in nature where plants do make use of nutrition through the leaf. It is a normal and natural thing that plants do in a range of different environments. Here's a few quick examples. Aquatic plants, ocean plants. I mean, kelp is one example, growing in that mineral-rich ocean water. It's taking up those nutrients through the leaf, and that's what's driving such high photosynthetic growth rates and such incredible biomass production that we see out of kelp plants, for example. Next example here is even dust. So we have some really interesting studies showing that dust, when deposited on the leaf, can actually be solubilized and nutrients can be absorbed from that dust. And it's through the pathway of the plants releasing organic acids onto the leaf. Now, everyone will be familiar with root exudates and the releasing of those various sugars, organic acids, amino acids, etc., which can solubilize nutrients from the soil. Well, same deal, plants actually can release some of the organic acids onto the leaf, and that's actually solubilizing nutrients off that off the dust, and taking that up through the leaf. And there was a really neat study that was specifically looking at phosphorus supply, and they showed that dust can supply meaningful amounts of phosphorus through the leaf from dust when the plants are phosphorus limiting. So they really do adapt and scavenge that nutrient when they need it. Next example would be animal wastes. And okay, I've got a picture of an insect here. It could be insect feces, which we have some great examples showing that plants absorb some of the amino acids and organic forms of nitrogen from insect wastes. But of course, through to our livestock, I mean, manure that lands onto the leaf, urine, of course, landing onto the pasture leaves. All of these nutrients are being taken up through the leaf if they land on the leaf. So animal wastes, absolutely a big source of fertility through the leaf. And then lastly, even fog has been demonstrated to supply ammonia gas, in which the plants can breathe in through the stomata and actually assimilate that nitrogen into their biomass. So look, there's just a few quick examples. Yes, plants are also able and adapt, and yes, they do make use of foliar nutrition as well in nature, and we're just going to try and mimic that and apply that knowledge across into our agro ecosystems for our production and quality kind of outcomes and goals. So how are some of those nutrients taken up through the leaf? And there's actually multiple pathways, and look, some of these are more important than others, so it's somewhat listed somewhat in order, but I guess with the caveat here just saying that point 1 and 2 there, through the cuticle and through the stomata, these would be the generally accepted dominant two pathways of nutrient uptake through the leaf. Now, the cuticle is that waxy layer, that waxy coating around the plants that helps them to conserve moisture, but that waxy layer is very malleable. It kind of tightens and loosens, it kind of bends, and it has these kind of micro pores and micro cracks and crevices within these kind of lipid layers. And so this creates this, it's actually quite a porous membrane when it's more open, where nutrients can actually pass through. So they do pass through these micro pores, And then, of course, the stomata, which open and close in order to help the plant breathe in carbon dioxide. When those stomata are open, they are also very able to take up nutrients, or particularly able to take up nutrients through those stomata. But even when the stomata are closed, they also can take up some nutrients as well. Now we have a range of other examples here, and it kind of depends. We have different examples in the literature, different crops maybe specializing in this more or less than others. Kind of depends on a case-by-case scenario. But for example, trichomes, this is some of the fine hairs on plants. At the base of those trichomes have been shown that the trichomes kind of catch the nutrients, funnel them down to the base of those trichomes where they're absorbed. And we have a few examples of this. For example, like sunflower has kind of been the real star of the show. A really strong affinity to absorb nutrition through the trichomes on sunflower. We have some other evidence around things like soybean, cotton, tobacco, and certainly some of the carnivorous plants as well, our insect-eating plants, etc. So they certainly do that through these pathways. The cells kind of adjacent to the veins in plants have been shown to have a little bit higher permeability, so they can absorb a bit better nutrition. There's other epidermal structures, for example, bark, even bark on trees has been demonstrated to absorb nutrition. And endocytosis, this is a process by which kind of the plants engulf in on themselves and their membranes kind of engulf and they absorb large macromolecules. So this would be more so the uptake for things like some of the kind of the proteins and bigger macromolecules, which can actually, and even microorganisms, which can be engulfed and internalized into the plant. So look, we have kind of mixed evidence across different crop types, etc., across these, but as I mentioned, the two kind of the main and primary pathways generally considered would be the cuticle and the stomata. And here's just a nice visual of that. There's your cuticle layer there. This is this waxy repellent layer under, and we'll come to this later on in the presentation, under dry air, under low humidity, you can see that cuticle becomes very closed or very retracted, and therefore it's not open to the outside world as compared to when we have higher humidity. These micropores, these cracks and crevices, they become more open, more loose, and which the nutrients can now pass through that. And there's our foliar droplet that is able to pass through, for example. And as I mentioned, stomata was the other pathway in which when those stomata are open, the nutrients are able to pass through the stomata, traveling along the guard cells, for example, and moving into the leaf. So this would be your two main pathways. Now, one of the other big advantages of the foliar spray is the speed of uptake. And this is one of the mechanisms which enhances the efficiency of those applications. Because again, the speed of uptake means the quicker you get the nutrient into the plant, the quicker your job is done. The quicker the nutrient is lying around in the environment where it potentially could be lost, locked up, etc., etc. So here's just two examples demonstrating the speed of uptake with urea and amino acids. On the left-hand side here, we have a urea uptake over time on two turf grasses here. And you can see how quickly it's within the first 2, 3, 4, 5 hours that the bulk of that urea is really taken up. It's very, very quick. And actually amino acids are even quicker. So in this study over here, they applied this particular amino acid here, glutamate, which you can see had very, very rapid absorption. Literally within an hour or two, we have the uptake of those amino acids. So, look now, nitrogen, these two forms of nutrients are particularly fast at being taken up. Some of the other nutrients are not necessarily as quick, but pretty much really within a 24-hour period, you're talking that really the bulk of the nutrients have been absorbed through the leaf. And that's a big part of their advantage, because if you spread fertilizer down into the soil, particularly dry fertilizer, if it's, again, dry conditions, low soil moisture, and that granule doesn't dissolve, it's going to be a really slow uptake. It needs to dissolve, it needs to wash down into the soil, it needs to be taken up by the roots and then used up in the leaf. So that might take a matter of days. That's if you get some rain, and who knows how long otherwise. So, in a liquid solution, which is already dissolved, applied onto the leaf, we see this much more rapid absorption within a few hours in many instances. So that's a big part of their gain, a big part of the benefit of the foliar spray. So, okay, this is really what we're trying to achieve with a foliar spray or with plant nutrition in general. It's to help the plant photosynthesize, to help the plant grow. That is how plants grow, and that's how we're going to support plant growth and development. So this is what really optimizing plant nutrition is about. It's about optimizing the supply of the micro minerals, which form part of enzymes which help to catalyze this reaction. And we're talking about, firstly, photosynthesis. It's CO2 plus water. And what the plant does is, incredibly using energy from the sun, stitches that CO2 and water together to form sugar, glucose specifically, plus a little bit of extra oxygen for all of us to breathe, of course. So it's really just this simple process of stitching CO2 and water together to form sugar, but we need essential macro and micronutrients in order to catalyze that process. So that's your first step of photosynthesis. Once we achieve photosynthesis, we have that sugar. That sugar is the building block or the carbon skeleton from that sugar, in which the plant then uses that sugar to stitch things together, to rearrange the carbon skeleton within that sugar, again, attach it and stitch it to other things, basically to do all sorts of fancy shape shifting and rearranging of those carbon skeletons to turn that sugar into all sorts of other molecules. Literally anything and everything that the plant is made up of and that it requires. So its body, its structure, so to grow its roots, its shoots, its leaves, to grow the cellulose, the lignin, to hold all of that up, for example, but also to produce some of the other internal phytocompounds and plant various kind of compounds, like the colors, the flavors, the smells, the scents, the defense chemicals, etc., antioxidants, etc., etc. So you've got all sorts of structural parts of the plant, but also the internal biomolecules in which are essential for plant growth and development. And again, in order to build all of these other things that the plants need, you require essential macro and micronutrients, which form part of enzymes which help to catalyze the secondary processes. And if you don't have these, you're not going to have this. So this is kind of where foliars plug into the story, is that it's a way to optimize plant nutrition to support plant growth and development, as you can see there, to support that process. And to do it rapidly with a quick injection of the key nutrients that are required, and to do that quickly and to support plant growth, particularly at key developmental stages. So look, it's not to say, again, you can't do that through soil. It's just that the foliars have a bit of an advantage in terms of that accuracy, precision, and speed. Okay, one more quick example of kind of how this plugs into some broader discussions around plant development is through the use of nitrogen utilization, nitrogen metabolism. And I won't dwell too much on this slide, but you can see here, it's really just talking about the plants, when they take up nitrogen, there's various different forms of nitrogen that they can take up. So nitrate is a common one, of course, urea would be a common one, and ammonium. These would be our three kind of main traditional forms. But when the plants take up those, they actually don't necessarily want the nitrate per se. They don't want the urea per se. They don't necessarily want the ammonium per se. They're all just also building blocks. They're sources of nitrogen, but the plants will expend energy to convert those sources of nitrogen into organic forms of nitrogen, so into amino acids, for example, and then stitch those amino acids together to form things like proteins, or they can be part of other molecules like chlorophyll, DNA, RNA, plant growth hormones, again, defense chemicals. So all of these other organic molecules these are nitrogen-bearing organic molecules, and they are the things that really help plants grow. These are the functional molecules that plants need and require, and that help and support plant growth processes. So nitrates are just a building block to get there. Same with ammonium, same with urea. They're just ingredients in which the plant can then turn into what it really, really wants. But in order to do that, in order to drive and push nitrogen along this metabolic pathway, you can see I have some additional nutrients here in red boxes. And these are the synergistic nutrients that work with that nitrate, for example, in order to help this conversion. So molybdenum, sulfur, and iron are key to convert nitrate down this pathway. Nickel is key to support urea down this pathway. Then we need magnesium and manganese to convert ammonium into amino acids. And then to build all of those other organic molecules, there's a range of different nutrients required. Particularly the top three are really important for protein synthesis: phosphorus, sulfur, and magnesium, but also manganese, boron, potassium, zinc, and copper all play a role in nitrogen utilization and the efficiency of the conversion of that nitrogen. And that's the other part. We often talk about nitrogen use efficiency in the context of nitrogen uptake efficiency, meaning of the amount of nitrogen that I applied, how much of that was taken up by the plant. And yes, that's a really important part of the nitrogen use efficiency discussion. But the second half of that conversation is, well, once I get nitrogen into the plant, how efficiently am I converting it into protein or into these other organic molecules that plants really require? So that's the nitrogen utilization efficiency. And in order to drive that efficiency, you've got to balance plant nutrition and make sure that you've got all of these other synergistic and complementary nutrients present. Okay, so in a nutshell, let's move on to some practicals. That's kind of just really the idea of using foliars to optimize kind of these key nutrients here or these key nutrients here. This is really what we're trying to kind of support the plant in doing. So moving on to some practicals. When designing a foliar mix, this might be a couple of key bullet points that I would start to consider. So firstly, you need to know what it is you want to apply. Like, what are the nutrients that plants actually need? What do they require? And that's where you might want to use a plant analysis, a tissue analysis, or a plant sap analysis, maybe a handheld meter, such as some of the emerging tools and technologies that are coming out in just the last few years. So firstly, we just need to determine, well, what are the nutrient imbalances? What are the limitations? What are the key nutrients that actually need addressing? I mean, this is fundamental kind of step one. Then we can move on to say, okay, well, what is the best source of that nutrient? Different fertilizer sources, different nutrient sources. Are there any complementary nutrients that need to come with that nutrient? And we've got to consider some of the antagonisms and incompatibilities as well. We don't want to be mixing soluble calcium and soluble sulfate, for example, in the spray tank. They could precipitate out, for example, to form gypsum. So we've got to be careful of some of the mixing aspects as well. Then you want to add some carbon additives, your general kind of chelating agents, carbon kind of synergists, things like molasses, amino acids, for example. pH adjustment becomes also very important. So as a general rule, around pH 5 to 5.5 is a general good optimum spray pH, final spray pH for nutrient uptake. And then lastly, things like maybe a wetter sticker or kind of droplet kind of conditioners. So we'll move on and talk quickly about those. So these would be kind of the 5 main things that I would kind of consider with your foliar formulation. So diving a little deeper though, I've put together this kind of framework, which I call F.A.C.E. Formulation, application, crop, and environment. And these are the kind of key factors that are going to influence the success of your foliar spray. And it's going to help us avoid this spray and pray approach. A good foliar spray is not just about, well, dissolving some nutrients, putting them in the spray tank and going. No, there are a lot of important details. Details matter. And these are the things that we really need to focus in on in order to ensure we hit that bullseye and achieve a good response from that foliar spray. So the response of that foliar spray, it really depends on these 4 things. the formulation, what it is you put in the spray tank. Yes, that's one piece of the puzzle. Secondly, how you apply it, the application considerations. Then we have the crop or the plant species is going to be next, as well as the environmental factors and some environmental considerations. So let's take a very quick tour through a handful of these as some key takeaways for you guys today. So formulation. Okay, this could be a long chat, but I'll just cherry pick out a couple of kind of key points here to make because there's a lot here to say. Water quality, though, I think is an under-discussed point in not only foliar nutrition, but also for pesticide applications as well. When we have poor quality water, that poor quality water can reduce the effectiveness of our foliar nutrition and reduce the effectiveness of our pesticide applications. So this is particularly true when we have kind of groundwaters, maybe very hard waters, very high pH waters. These are full of things like carbonates, bicarbonates, calcium, magnesium. Sometimes waters can be high in iron, sometimes high in aluminium, could be all sorts of things, in which, in essence, these are contaminants in that water. So that when you dissolve nutrition into that water, those contaminants start binding to your nutrition. Or, for example, start binding to your pesticides. And that can actually start to tie them up and render them unavailable and less effective before you've even gone and applied them, while they're still in the tank. So you really do need as clean a water as possible. So if you can, you want to try and invest in saving and storing rainwater. That can help. And even if you can't use 100% pure rainwater for your foliar applications, even if you could use it as a dilution, so at least cut your groundwater by 50-50, that's going to lower some of those contaminants, dilute out those contaminants. So any way in which you could kind of store some rainwater or snowmelt, that's going to be advantageous. Your next option would be something like reverse osmosis, and this can also, of course, help to pull out all those contaminants, so you're left with very, very pure, very, very clean water. And that can also be, again, very helpful. And lastly, I would just emphasize, if you can't do my lowest hanging fruit here, if you can't do rainwater or reverse osmosis, we have to kind of talk about the spray pH here. And this is where I would recommend adding something like citric acid to the spray tank water first and foremost. So you're going to fill up that spray tank, about 3/4 full. And then you're going to add something like citric acid would be my weapon of choice here. But look, I know folks use acetic acid or other organic acids. Some folks even use AMS, ammonium sulfate. Any of these are okay. I have a personal preference for citric. I think it does well. And what that acid is going to do, it's not just about lowering the pH, it's about tying up and binding those contaminants, and therefore we lower the pH. So you're kind of somewhat cleaning up the water a little bit by acidifying it first to render some of those contaminants less active. And then you can add your foliar nutrition, your nutrients, carbon chelators, etc., etc. But you just want to kind of clean that water up first with some acid. So that's kind of key points there around water quality. The next point is that point about spray pH that I mentioned. You kind of want that final pH to be around about 5 to 5.5 in that kind of window as a general rule. Look, there's wiggle room there. I know farmers that often have mixes that are much lower than that, sometimes a bit higher than that, but look, as a general rule, I would always try to be at least below 6. I think 6 would be my real top end. And we'll touch on a few of these other points as we go through, but also just wanted to mention the role of some carbon additives or chelating agents. They are nutrient synergists. They really just help to make nutrients work better. So let's kind of dive a little bit into a couple of examples here. So when I say carbon-based inputs, look, the idea is simply visually represented really nicely in this slide here. Rather than apply the nutrient on its own, we're going to combine it with a carbon source, and that carbon source has all sorts of various properties and benefits, but particularly, for example, it can have a lot of these kind of charged sites and surfaces, and that can bind to or chelate or complex the nutrient, so wrap up the nutrient. And that helps to stabilize the nutrient. That actually helps to prevent some of these lockups or precipitations in the spray tank, so it keeps nutrients kind of separated. But those carbon molecules also help to actually enhance the uptake through the leaf, particularly stronger chelating agents. They have the ability to support the uptake of that nutrient through the leaf. So we get better uptake of the nutrient through the leaf as compared to when it's in its pure kind of salt form. So that's in essence what chelation is. It's really about binding to the nutrients, the essential nutrients, wrapping them up and neutralizing the charge. And when we neutralize the charge of the nutrient, that's what helps to support the uptake through the leaf. So we get better absorption through both leaf and soil, to be fair, or through roots, sorry. Chelated nutrients also, particularly around amino-chelated nutrients, they are much more mobile within the plant. Chelated nutrients have lower salt index, so less risk of burning, and they can also provide, in some instances, a bit of a slower release mechanism. Now, molasses, as an example, does contain some organic acids and some amino acids within it. And that part of the molasses is a bit more of a chelating function through those organic acids and amino acids. But the sugars that are much more dominant, of course, in molasses, they are much more helpful for the nutrient transport within that plant as well. So molasses has, as we'll move on and talk about, has a few multifunctional benefits about it. So chelation, carbon-based additives, it just helps nutrients work better is the key kind of point. Now, in terms of another aspect of the formulation is the water quality is the surface tension. So the surface tension, of course, is that tendency for water molecules to bind to each other and create that very insular interrelationships with the water molecules. So that can start, practically speaking, that makes water start to kind of more bead in on itself, as you can see here on the left-hand side. So by reducing the surface tension, by adding surfactants, we can help those water molecules to spread out and actually increase the surface area of that droplet. And now we have a big surface area here where the nutrients can be absorbed, as compared to this droplet that has a much smaller surface area under there. So again, sugars and the organic acids that are found in molasses, they essentially are inserting themselves in between the water molecules within the droplet. And so that's, of course, going to disrupt that hydrogen bonding between the water molecules, keep the water molecules apart, and therefore keep them all spreading out, reducing that surface tension. So that's going to improve the droplet spreading across that leaf surface area. So it's really about them being bulking up the droplet, increasing the density of the droplet with all of those acids and sugars inside that droplet. And this is just another slide kind of really emphasizing the same point. There's been some really interesting studies looking at how we can kind of measure the droplet adhesion and these angles in which they adhere to the leaf, and with the obvious point that you can see this droplet here is just has such high surface tension there. It's really has a low surface area at the bottom of that droplet in which it's connecting with the plant, as compared to this one here, which is nice and spread out. This droplet is spreading out, and we have a very different angle of which that droplet, that bubble is, which is impacting its surface area underneath for uptake. So again, higher surface area, more contact with the leaf surface area is going to give us more surface area for uptake, and that's going to improve foliar nutrition performance, of course. Okay, so other points on the application. It's about your droplet size, droplet quality, droplet deflection. So of course, what nozzles you're going to use, what is your spray pressure. We don't want too much pressure so the droplets bounce off. We don't want too little pressure so they don't reach the target. The surface area of the plant canopy, how much area do we have to cover? What's our speed? Not too much volume of water. per acre, so we're not kind of dripping and running off, and of course not too fine a droplet sizes, so it just drifts off in the air. So these are some of the challenges that are and considerations that are really important in the application of that foliar spray. And that's where we have also conditioners that can also improve the droplet quality. So for example, a humectant is a substance that that helps to retain moisture on that leaf surface. So by attracting and holding moisture from the air. So in essence, when those droplets land on the leaf, the quality of that droplet starts to determine how well the foliar and how much time the foliar nutrients have to be absorbed. And if that droplet dries out really quickly, then the nutrients don't have time to pass through the leaf. So we want to slow the droplet drying time a little bit to give the nutrients time to pass through the leaf. And that's what humectants do. They attract moisture in from the air, they attract the humidity in from the air, and that helps to keep the droplet wet and therefore slow the drying time. So prevent the droplet from drying too quickly, giving that nutrition time to be absorbed. And it's the sugars that we find, particularly in molasses, which are hygroscopic, which means they have this property to attract and hold water. So it's the sugars that particularly are providing these humectant properties or humectant benefits within a foliar spray mix. Now, similarly, spray drift is an important consideration. Many farmers will be well aware of this. And again, it's the sugars and just the amino, it's all things here, the aminos, the organic acids, and the sugars that are within molasses that actually increase the droplet weight and viscosity. So again, think of a droplet of just nutrition in there, soluble nutrients. Well, if we pack that droplet and add all these additional sugars, organic acids, amino acids, etc., and we increase the density now of that droplet because we've packed it full of all these other carbon-based compounds, that means the droplet is heavier, and that means it's going to fall faster down to the target. So it's not going to be picked up in the wind. We're not going to drift off through that wind. We've got a nice, dense, heavy droplet that's going to come straight down and land on the target, which is exactly where we want it to land. So it's about heavier, denser droplets. And then, of course, molasses is a little bit sticky, as many farmers will be well aware if they've ever tried to use it in the middle I was going to say the middle of winter, but you wouldn't be using it in the middle of winter, but in the colder times of the year, in early spring. Of course, it's a very dense, thick, viscous liquid, and it's very sticky, and so that stickiness helps to help it adhere to the leaf surface. So better sticking means, again, we have more time for that nutrition to be absorbed in case maybe there is a rain around the corner, or the next day some of that nutrition might get washed off, but with a wetter sticker there that molasses really helps with, we can improve the stickiness and therefore the uptake. Now, more stick on the droplet also means less droplet bounce. Okay, so it's that the droplet size, the forward speed, the pressure. If we have too much of that, those droplets could bounce off the leaf. But when we have that, all of those sticky sugars in there, that helps to stick that droplet and prevent some of that bounce and shatter. So again, it's all about droplet quality, improving droplet performance in terms of reaching the target as well as the other chelating and benefits that we talked about, but also in terms of the droplet quality. Now, look, different plant species, different crops are more or less responsive to foliar sprays. General kind of key points here would be that younger leaves are a bit more tender and more responsive to foliar sprays than are older leaves. It's not to say that older leaves don't absorb nutrition, they sure do, but just those younger leaves are particularly primed and advantageous. And the leaf surface area is, the leaf surfaces are negatively charged. And that's that point about the chelation, the chelating agents that help to neutralize the charge of the nutrients, is that when we apply those, that neutral charge is able to pass through the leaf much more effective. Because the leaf surface is negatively charged, if we apply a cation, we have this kind of strong attraction and we get this kind of clumsy, sticky, slow, inefficient uptake. If we apply an anion, a negatively charged nutrient, to a negatively charged leaf, we get this repulsion, and again we have slow and clumsy uptake. So the best way to overcome some of this chemistry of the leaf surfaces is with those chelating agents, as I mentioned earlier. Okay, environment, and this is also a really important piece of the puzzle. The environmental conditions as to when you are applying the foliar spray is also really important, and the big one here is humidity. I mean, it's humidity and temperature, they go hand in hand here, but the key point here is that humidity, high humidity, means the plant is going to be more open, more open and not so tight and closed. And we want it to be more open and more porous so that those waxy cuticle, we have those micropores that can pass through, so that the stomata are open, that nutrients can pass through. So we want the plant not to be hot and dry and stressed and tight and conserving moisture and closed. We want it open for business. We want it to be open and porous. So that just really means high humidity is your optimum for the timing of the application. So early morning, late afternoon, for example, is going to be better through into the evenings. The magic number here is around about 70% humidity is like excellent. You can achieve uptake lower than that, but if you're at 70 and above, like this is perfect for foliar uptake. Now the temperature, of course, plugs into this. Look, on a technicality, a bit of research that's been done on this would say kind of max 82 Fahrenheit, which would be, say, for anyone else watching, 28 Celsius or so. I kind of think that that's a real top end. I think it works a bit better, a little on the cooler side. So maybe a max of around 77 or 25 Celsius is I think preferable. If you, again, sometimes, we've got to be practical and we've got to be pragmatist in some of this. And look, in some instances, maybe the perfect conditions are not always feasible, but there's no harm in knowing what the optimum conditions are and aiming for those, or prioritizing certain fields under those optimum conditions. And look, I know that we have to be practical and sometimes you've got to get on and get the job done. But anyway, those are the kind of, I would say, my optimum kind of temperatures around about a max of kind of 77, I think is a bit better. But that said, when you're going to add those humectants, that's where the molasses again can help. That's going to help to pull a bit of extra moisture out of the air, increase the micro humidity in that micro canopy, in that micro environment of the canopy. We can kind of increase the humidity, especially if we use slightly higher water rates as well. That can also just give us a little bit of extra humidity benefits as well. Wind, a little bit of wind can be favorable. Actually, that helps with that kind of nice little bit of drift and that swirl and undercoating the underside of the leaf surface. And I'm hearing some really interesting things just in the last year or two with folks now experimenting with foliar applications through the drone. And of course, drones with that wind from the propellers creating this little vortex and this underswirl, getting really good coverage and coating both on the top and the underside of the leaves. So that's kind of, that little bit of wind can be actually quite a favorable thing. And lastly, look, from a drought stress point of view, plants that are drought stressed, that are struggling to get moisture and nutrients out of the soil under drying soils, they actually benefit a lot from a foliar spray, particularly in the earlier stages of drought stress. However, once we move into the plant really in the latter stages and the plant really struggling and kind of dying off, look, of course, look, a foliar spray is not going to save your bacon there. But look, in terms of early stages of drought stress, when the plant root uptake is a little impaired, a foliar application can be very advantageous. Now, just a quick plug here on humidity and temperature, just to flash this one on the screen. If anyone's not familiar with this, you can Google image this one, Delta T. I'd highly recommend it. It really plots this relationship between humidity and temperature. So you can just look up your, yeah, you guys would have to look up for a Fahrenheit version here, but you just look up your current humidity and your current temperature, and you follow those two lines across. And if you're anywhere in this kind of green zone here, this is good for foliar spraying. Okay, so you can use Delta T if you're between 2 and 8 there. That's anywhere in that window is good conditions for foliar uptake. And again, I just will emphasize this importance of humidity and the timing. And this is just another visual to that. It really is such a key point. Here on the left-hand side, we have low humidity. Here's kind of hydration within the cuticle. That cuticle being, you can see a lot more closed and retracted, tightened, closed. So any of the kind of the hydration within that cuticle, you can see it's all pulled down very low to the surface here, whereas here where we have high humidity, or for example this is from underneath this droplet or the bubble, we get this better saturation of moisture through this flexible waxy cuticle, and you can see what that has done is create these bridges from the outside to the inside. We've created this bridge of hydration where the nutrients and solutes can pass and move. So that's why we want high humidity, high water saturation of these flexible, permeable cuticle layers. And now we've created this bridge to get across for the nutrients to pass, unlike here where all of that water is very retracted at the bottom, at the base there, which is limiting the nutrient uptake, nutrient pass through across the leaf. Okay, so in summary, we've talked a little bit about a range of different approaches to foliar feeding, the whys, the how, some of the plant nutrition aspects, some of the foliar design, the F.A.C.E principle, for example, the formulation, and these environmental factors. These are kind of some of the key messaging if you're really going to go down this foliar pathway. These are some of the key kind of takeaways from this, and with a particular case study around molasses today, and as one additive in the formulation. Just to summarize here, we talked about its ability to improve the droplet quality, so the density, the viscosity of that droplet. We talked about how the sugars there can also improve the stickiness, the adhesion of those droplets onto that leaf. That's going to improve, therefore, target reaching, nutrients reaching the target. It's going to improve uptake. That's going to improve your spray performance. Some of those sugars additionally can also help to improve microbial activity on the leaf. So that's going to help to feed some of the phylosphere biome. And also some of the sugars actually in molasses have been demonstrated to reduce plant stress and phytotoxicity. And that's from things like pesticide sprays. So some of our selective herbicides, selective chemistries can still have a stress-inducing response on plants. And the sugars in molasses have been shown to reduce some of that stress from pesticide exposure, as well as some of the other environmental nutritional stresses as well. So in summary, look, it's a multifunctional, multifaceted ingredient, a bit of a good all-rounder.